I hope the slides are also visible, right? Arpit?
Yes, sir, it's visible.
Well, so uh, in last class, that means in yesterday's class, so we basically tried to understand how the bands are forming from discrete energy level of individual atoms in case of your solid state material. So then we discussed uh, how we can get the carriers, so how we can get the electron and the holes, and as well as we have also seen that with the doping, we can control the number of electron or hole ratio, concentration ratio, we can control by doping, because with the temperature we'll get equal number of electron as well as hole. So whenever we'll break any covalent bond, so we'll give one particular electron and hole together. But for fabricating typical device, we need different type of material, like where we have dominatingly, let's say, electron, or we have mm, holes as a majority carrier. So to do that, we need to dope it. Now, when doping this material, this semiconductor, in case of elemental semiconductor, that means silicon or germanium. So we are doping like p-type doping if you want. So we want to incorporate group 3 material, that means arsenic, that means aluminum, gallium, or indium in the silicon or germanium crystal. Now, when doping, we'll get this hole as a majority carrier. At the same time, we'll also get ion. So we'll also get negatively charged ion. And remember, this ion cannot move in semiconductor, or not only semiconductor, in any solid state material. But remember, anyway, I think you know, in battery. So battery, anyway, now a lot of research is going on for this electric vehicle. So in battery, in liquid medium, these ions can move. But these are all solid state materials. So in semiconductor, this thing will only discuss this solid state material. So these ions cannot move. That means although they have some charge, but they cannot move. But remember, in order to have current, we need movement of charged particle. So the charged particle should move if you want to get current, fundamentally. So that is why these ions will not contribute to your current eventually. So, but the carriers, that means electrons and the holes, will participate. So then another important conclusion we discussed yesterday, that breaking a covalent bond, just if you want to break particular covalent bond in all this semiconductor, because semiconductor we are having mostly this covalent bond. So just breaking a covalent bond is lot difficult than breaking a bond and making another bond. So because when the holes are moving, essentially these holes are moving with the as a effect of breaking a new bond and making another bond. So in this way, actually your bonds are shifting, and essentially we are treating that a positive charge is or the vacancy of electron is shifting. So fundamentally, these are the concepts. So then, okay. So the last topic that we are trying to discuss now, what is the effect of temperature on this semiconductor? So as we know that in case of pure semiconductor, That means intrinsic semiconductor. So where we have no doping as well as there is no defect. So in case of intrinsic semiconductor, we have no doping as well as no defect. So in pure semiconductor, to break any bond, covalent bond, we need to heat up the semiconductor. Like we need to increase the temperature. Now our objective is to understand how the number of carriers will increase with the increase of temperature in case of your pure semiconductor. That means intrinsic semiconductor. So let us try to understand. So so this is a T and this is your carrier concentration, maybe electron or hole. So anyway, so here first we will discuss this intrinsic semiconductor. That means the semiconductor without any doping, a pure semiconductor. So essentially, if we start from 0 Kelvin, so at 0 Kelvin there is no thermal energy to break any covalent bond. So that means there will be no carriers at 0 Kelvin. Now, if we keep on increasing this temperature, so then the number of carriers will keep on increasing. And this increment behavior is exponential. And why this is exponential, that we'll understand in the coming slides or coming topic. So this is in case of your intrinsic semiconductor. Now the next point is how the carrier concentration will change with the change of temperature. Now to understand this, let us take the help of this particular diagram. So if we consider that our semiconductor is n-type doped, let's say we have silicon where we have doped this silicon using arsenic. So with the arsenic, this silicon become n-type. So that means this arsenic has that 5th electron, which it will contribute as a carrier. So now from this diagram, so at 0 Kelvin, when even after doping, so at 0 Kelvin, there is a like this electron is still attached to your arsenic atom, because at 0 Kelvin, from this figure you can understand, again in the last class also we have also derived that to take out this electron, this 5th most electron from this arsenic atom, we need to provide this much of energy. Although this is a very low energy, 0.1 electron volt typically in case of silicon and arsenic. So that means the energy difference between this this donor this level and the conduction band is 0.1 electron volt. So this is a very low energy. That means very low energy is required to take out this electron. Now with this concept or with this statement, so what will be the behavior? So if we keep on increasing the temperature from 0 Kelvin in case of arsenic doped silicon. So since obviously it will start increasing, and now what will be the behavior? Whether it will take this nature, or it will just abruptly increase, or what will be that? So it will increase rapidly initially. Why it will increase rapidly? Because see, the energy difference between these two level is only 0.1. So with very low amount of thermal energy at very low temperature, so you will be able to get this lot of carrier, because that energy ED to EC difference is very small, of the order of that 0.1 electron volt. So it will increase like drastically. So then it will saturate. So why it will saturate? So then what is happening? So most of the arsenic atom or the donor atom will donate that 5th most electron. So now this carrier concentration will remain almost constant. And after that, after a certain once again, after certain temperature, once again it will it will start increasing. So in case of, so this is this behavior in case of intrinsic semiconductor, where without doping, intrinsic, and this blue line is in case of extrinsic. Extrinsic. So and now I think once again, so in case of doped semiconductor, since this dopant level is very close to that conduction band energy, so that will donate your electrons rapidly. Now after all the donor atoms, when they will donate that fifth most electron, so then the concentration of carrier will remain constant for a certain period of temperature. After that, after a certain temperature, so once again this covalent bond will start breaking. So then it will follow that same intrinsic behavior. So because in intrinsic, the carriers are coming due to like only this breaking this covalent bond. So it is not that key, that fifth you have any atom with the 5 electrons, and that fifth loosely bound electrons you have in case of intrinsic. So then after this certain temperature, so this extrinsic semiconductor carrier concentration will also increase temperature similar to your intrinsic semiconductor. Now next point is, see which domain will use to fabricate our device, like at which temperature will operate our device to get to get a particular function. So at which temperature range? So because if we identify roughly, so this is domain 1, let's say, and then this is a domain 2, and this is another domain 3. So now which domain will use, or which temperature range will use to operate our device made out of this doped semiconductor, this extrinsic semiconductor? So from your understanding, I think you can like you can guess that we'll use, or we are using our semiconductor in this particular in domain, like when our temperature range is within this second domain. Why? Because in this temperature range, the carrier concentration is constant. So now, so here I have not mentioned other temperatures. So typically here we have, in case of silicon and this arsenic material, here we have room temperature, that means 300 K, and also obviously at high temperature it is difficult to use, because the with the so there are certain reason. So one is, see, with the when you will operate our device, like when you will operate, let's say your FET or MOSFET. So when you will apply some electric field, there will be some your resistive component, and then there will be some IR loss. So that IR loss will essentially heat up your device. So now when you are operating, your device is getting heated up. Anyway, you have observed this in case of your, like you know that your laptop, mobile, all the electronic components are typically getting heated up when you operate. So now if we, let's say if we use this temperature range, so what will happen? So with the slight change in the temperature, the carriers will change drastically. See, this is exponential increment in the carrier concentration with the temperature. That means, let's say we are operating anyway, these are all high temperature, but still, so if there is a, let's say, 10-degree difference in device, so then the carrier concentration will change drastically. So then it will change the overall device performance. So that is why this domain is not desired domain, that this temperature range is not desired temperature range to operate our device. But here you can see this is a constant. So with the drift or with the change in the temperature due to its heat, so there will be no as such change in the device, because you know this is a carrier concentration, and carrier concentration will change all the other parameters of your device. So this is the reason, one reason. Another thing, what about this region 1? So can we use this region 1 at all or not? Because again, this is very low temperature region, and this particular region we are like typically people are using for cryogenic application. Cryogenic means, you know, this recently this quantum computer and all these applications are coming where we need to operate our device or this electronic system at very low temperature to observe those quantum this qubit and all other operation anyway. So those devices, so we are using, so we can use this this domain also, but typically we are not using, like in normal MOSFET diode, in normal application we will not use, but for cryogenic, like this typical application, we can use this domain. But in that case we should confirm like what is the requirement, carrier concentration requirement at what temperature. So it should be defined very well, otherwise there will be, once again like this, there will be change in the carrier concentration with the slight change in the temperature, and then you may not get the desired performance from your device. So this is the your overall carrier concentration change with the temperature. Now moving forward, so okay, so these are something which we have discussed. So how the bands are forming from the discrete energy levels. So these are I have taken from the SMG book. So you can go through those discussed slides or those annotated slides, or you can also follow this book by SMG. So here also this is again the discussion that we made previously, considering the diamond lattice. So here you can see this is 1s, 2s and 2p6. So because diamond has 6 atomic number, so in case of silicon we have atomic number of 14. So again here we have this 1s, 2s, 2p6. So we are not using those. Okay, so another interesting thing, why we are not interested in those energy level, why, let's say if we consider this particular, so why we are not interested in electrons within this energy band, in this 1s orbital. So the reason is, see, to take out any electron from these bands, it requires very high energy. So that is why in all this discussion we'll only discuss, or we'll discuss this conduction band valence band forming in this outermost this orbital. So these, to take out this electron, it requires a huge energy. Mostly anyway, this X-ray, you need very high energy, like X-rays type of energy you need. So there are application. So that is different anyway. So this is the in case of silicon. Now this is the after I think in the last class also we discussed that how, again I think you know this, how in terms of band, that conduction band and the valence band, how we can explain the conductor, insulator as well as semiconductor. So so this is okay. So here actually you know this band gap now this is forming at a particular lattice distance, which is lattice constant. So now this, how to measure this band gap? So there are different techniques. So you can utilize this light absorption technique to measure this band gap. So whenever you know this, you will excite your semiconductor with some light. So then your one electron from the valence band will move to your conduction band. So then looking at this absorption, so at which wavelength you are having this absorption of your light, so you can determine the band gap. So again, for all the materials, you cannot determine band gap in this way because there are certain reasons that we'll see. But this is typical way to measure the band gap of your semiconductor. So these are something which we have already discussed, and this is also something we have discussed, like how the energy of electron and the hole are changing, because um, in band diagram, when you will increase the energy of electron, so it will move up. So the kinetic energy of your electron kinetic energy will increase, like in this direction. So this is the electron energy. Now at the same time, if you increase the energy of hole, so this holes will go down. So this is again with if we try to understand using that analogy. So this electron is like a droplet, or this in that water filled tube analogy, where we have discussed that these electrons you can consider as water droplet, whereas this hole you can consider bubble in the water. So you can so this is simple analogy anyway. So here you can see like holes will float up like bubbles in water. And because a hole will always try, okay, so they will always try to take its lowermost energy. So this both electrons as well as hole will always tend to seek their lowermost energy. So that is why, so electron will always try to fall from this top to bottom in this energy band diagram, and holes will try to float up, because as with the analogies as like a bubble in the water. So then again, as we started the discussion, because all the semiconductor problem can be discussed using the bond model, which we have seen. Then as well as we have also discussed this band model, how the bands are forming. Now to discuss this semiconductor, this all problem in more detail, we need band structure. So this is how this band structure looks like, and how this is coming. What is the why suddenly this parabola is coming into the picture? So it is coming from the same that equation, that kinetic energy equation, that E equals to, so the kinetic energy of free electron, if we consider E equals to E square by 2m naught. Now this is, again you can see that this is the equation, like this is the parabola, and this parabola is the equation from where it is coming. This is the equation, kinetic energy of free electron. Now inside crystal, when your this electrons will move through the conduction band. So this is again, this is the conduction band. So this is a typical band structure and the conduction. So from where you will have your electron. So now when your electron is in the conduction band, so if we once again just draw that. So when you have excited one electron from the valence band to conduction band, so these electrons here you have free, so it is a free electron, it can move. So this is not bounded electron. So now it can take this kinetic energy, or it can have this kinetic energy. Now inside crystal, when this electron will move around, so there is a periodic potential. What is the source of that periodic potential? Because once again, see, we need to take help of all this concept. So once again, you know that we have, as for the bond model, we have all these atoms sitting in the crystal. So all these atoms has this nucleus. So when this electron will just move within this crystal, so there will be a periodic potential. Why this periodicity is coming? Due to this periodic atomic arrangement within the crystal, and those nucleus will create that potential. And due to this variation, or due to this change in the potential, periodic change in the potential, this electron mass will, so this this is a here I have written m naught like free electron mass. So but when your electron will move through the crystal or through the solid state material, so it will not have this free electron mass, because it will experience that potential, that periodic potential which is arising due to the atoms or the nucleus or the periodic nucleus in the crystal. So now if we so just to count that effect, that periodic potential effect, so we need to represent this equation a little differently, where we'll write this mn instead of m naught. So sometime in some book you will find this is written as mn. In some book you can see this is like m star, something like that. So what is the name of this mn? It is called effective mass. So effective mass of your electron, n for electron, and if you have mp, that is, so if you have P, so that means this is the effective mass of hole, because hole will also once again experience the similar periodic potential when moving within the crystal. So now if we try to quantify this effective mass, so from this equation we can easily quantify or this effective mass of your electron or hole. So it will look like something like this. So simply if we take double derivative of that equation, sorry, sorry, sorry. So if we take the double derivative, and it will be 1 upon. So essentially your effective mass is the double derivative, inverse of double derivative of your energy, this kinetic energy with respect to momentum. So this is simply the double derivative of this particular function, and 1 upon double derivative. So now from this this particular equation, what is the significance of this equation? So the significance of this equation is, see, now from this nature of this graph, so whether this is so if this is this parabola is a bit narrower, or if this parabola is little flatter, so looking at this band structure, you can easily calculate how, what is the effective mass and what is the significance of effective mass. Because see, in the coming this slide or coming topic, we'll see this effective mass is the mass with which your carriers will move around. That means you know this in current and everywhere. So when we need to calculate, or we need to consider the mass of electron, so then we'll consider this effective mass. Now if this effective mass is high, so that means you have a heavier carrier, so it will not move easily. So the mobility and all other things we'll see, like it will not be like very good, like if we have heavier mass, like simply like if you are like heavier carrier, it will not move easily. So that is why, so for now yeah, now we can understand, like for high speed application or like high frequency application where electrons needs to move very fast, so there we need some material within which your effective mass of electron or carrier is very small. And how to understand like which material will have lower effective mass? From this band structure you can easily understand. So you can, from here you can see, like your narrower is the parabola, so then your d2e and dp2 will be larger, and then your inverse of this d2 e by dp2 will be smaller. So then narrower will be this band structure. So you will have lighter electrons. In this case, this is an electron conduction band. So then lighter will be the electron, and then you will have faster and faster device. Now, if now from this discussion, just I will conclude this discussion. Now, if I give you, let's say, this three material which has a conduction band structure, this one, this is two, and this is, let's say, three. Now, looking at this band structure, you can easily tell me, or you can easily explain which material is suitable for high frequency or high speed device application. Because in high speed device, you need a lighter carrier. So this particular, this material 3, like with the material with this narrower band structure, conduction band, narrower conduction band, this is the most suitable one from these 3 materials. Okay, so this is all about your this effective mass and this band structure. So that is why so again, now if we look at this another representation of semiconductor problem in terms of this conduction band, valence band, this flat conduction band, or this valence band or bond model. So this quantification, so how like whether electrons or the carriers will be heavier or lighter. So these are the conclusion you cannot make from this other model, but from band structure you can. So that is why I mentioned, like with this band structure, again, this is not this is also very, I would say, like very simplified band structure. So actual band structure is a lot more complicated. So now this is a conduction band or the electron behavior, which will decide your electron behavior. Now this is your conduction, like conduction band structure and this valence band structure. So you can see here. So again, as you know, that hole is just the inverse representation of your electron. Again, in this figure also you can see, like it is just the inverse or just the flipped parabola, which we considered in case of electron. So this is for hole, which is representing once again this valence band. So now from here also you can see like this. Look at this. These are the effective mass. So this is the effective mass of electron here, and this is the effective mass of hole. So now M naught is the free electron mass. So you can see this is this is a bit flatter curvature or parabola compared to this conduction band. Now due to this, you can see here the electrons, which will essentially sit here when like after getting excited from your valence band. So then this electron will have lower mass because it has a narrower this band structure. But here the holes will be heavier, because you can, from here also you can see the effective mass of hole is higher than the effective mass of electron, because this effective mass of electron is the 1/4 of free electron mass, whereas the hole mass is equal to the free electron mass. So now we can once again understand like how this band structure and this parabolic this behavior will decide whether your electron and will be heavy or light, and whether how easily it will move within the device and what frequency. Remember, lighter is the your carrier. It will operate at high speed or high frequency. Okay. So now you can understand, like if you want to let's say fabricate some transistor for this let's say for upcoming 5G application. So there you need this some material where you have this lighter electron mass. That means you, for this 5G application or this upcoming high frequency application, you need some material where you have this band structure, narrower band structure. Okay, so then you will have lighter electron, and that will be suitable, more suitable for your this 5G application. And actually that is why for this upcoming 5G or 6G, silicon will not work. So anyway, that's a different discussion. So that is why people are moving out from this silicon and going to this compound semiconductor. Okay, so this is a little bit more detail of this band structure, what we have just seen in the previous slide. So here you can see you have this p equals to 0. P is the momentum. P equals to 0 here, and here we have one direction, and here we have another direction. What is this meaning? This 100, 111, and 100. Again, I think one of you asked in the last class, I guess, what is the importance of Miller indices? So this is actually the crystal direction. So this in the parent in this bracket, you know, this 100, it represents this crystal direction. So in case of this qubit, if I want to just quickly draw. So this 100 is this direction. This again, this is a plane 100 plane direction, like it is the family of 100. So this is these are all this 100, and which direction is 111? 111 is this direction, from this diagonal, this corner to this corner. So this diagonally, if you come at, so then you will go in this way. Now, what is why this is changing? Like why we are considering this two direction? See, in just for this, this is for silicon material, and this is for gallium arsenide material. And in both the cases, you have this is the band structure in case of hole, and this is the band structure in case of electron. So this is your conduction band structure. This is valence band structure. And now if you see this, or if you just compare these two figure, you can see this minimum of conduction band, the minima of your conduction band in case of silicon. If you go towards this 100 direction, you will find the minima. But at p equals to 0, you will find the minima in case of like conduction band minima in case of gallium arsenide. That means the electrons sitting here, or the electrons adjacent to this atom, in case of gallium arsenide, so in which direction it will go? So in the all direction, the mass, electron mass, everything will remain same, because it is, you can see here, like the conduction band, this minima is coming exactly at the 0 point. So here also you have the same portion, here also you have same portion. But in this silicon, so if we go towards this direction, 100 direction, you will find the conduction band minimum. So electron, in case of silicon, based on the direction of the crystal, it will behave differently. So that is why we need to consider all this plane, or this direction, or this Miller indices. So because you can now, this is another way, like if we don't know this Miller indices, or this thing, this concept, then we may not be able to explain this behavior, because it has been again observed also, like in different crystal direction, in case of silicon, the electron or carrier will behave differently, and this is the reason in terms of band structure. Okay, so another thing from here, just in case of polar material, just anyway, just for your information, polar material means, you know, this where non-polar material is, you know, the silicon. In case of silicon semiconductor, you have your covalent bond between two silicon. So these bonds are not polar. There is no ionicity. But if you take this, let's say another material, let's say gallium, the compound semiconductor, and this nitrogen, there also you have this covalent bond, but here it has some polaricity, because this nitrogen is more electronegative than this gallium. So this you know, these bonds are more attached to this nitrogen, and then this overall bond has some ionicity. So the material which typically shows this polar behavior, so it has this kind of this kind of band structure. this where you will find conduction band minima at p equals to 0 or momentum equals to 0. So now, but in the material where there is no polar this behavior of your bond, so then there might be there is a possibility that you will get this kind of band structure. So another thing, and perhaps the most common thing from this band structure is this material is called indirect band gap semiconductor. Why? Because in this silicon, when your electron from the valence band will move to conduction band, so see first it will have like first let us try to discuss this in case of gallium arsenide, because this is called direct band gap semiconductor. So because if we excite electron from the valence band, it will directly go to your conduction band. Only the change that is required in terms of energy of electron. So the when electron will move from the valence band to the conduction band, the change will be in terms of energy. But in this case, in silicon, see, if you want to move one electron from the valence band to the conduction band, not only you need a change in energy, but there this electron should have some change in terms of momentum. So there will be this change in terms of this is a momentum change of your electron, and then there will be this change in the energy. So both these are important, and that is why this exciting some electron from valence band to conduction band in silicon is very difficult, and that is why getting optical devices, getting LED out of this silicon, which is essentially indirect band gap semiconductor, is difficult or is very inefficient. Because see here, if you like in case of LED, what is happening, like when so these electrons are jumping down from your conduction band to valence band. So in this case, in silicon, you need a change in the energy as well as the change in the momentum. But in this gallium arsenide, if you make your LED out of this gallium arsenide, directly this is when your electron will jump down from your conduction band to valence band, it will emit this light. And so that is why these direct band gap semiconductors are very useful for fabricating LED or like optical devices, and silicon is not. So that means the LED you see around, I think you know, you have seen, you are using LED. So those are not made of silicon typically. So this is one concept. What is the time? Okay, we have some time. Now this is the concept of all your bond model, band structure, and this band model. Now in our electronic device, so we are primarily concerned with the current voltage characteristics. So that is called, once again, this terminal characteristics. What is the voltage will the voltage will give, and what is the current we are getting. So typically in this current, you know, this is the, if this is the current density J, it depends on the this is the velocity of carriers due to the applied voltage or electric field. So then this voltage of your this velocity of your carriers is once again related with your, this is the electric field. So electric field means the voltage per centimeter that you are applying across your device. And so this is the current density, and then how it is related with the applied voltage. So J equals to NQV, or you can NQ mu E. So this E is the electric field that you are applying from the outside, and this is the constant electronic charge. And so your current will essentially depend on how many carriers are available within the your device, and how easily it will move within the device. Again, this is one type of current. So there are different type of current which we'll discuss in detail in the coming module. So just roughly, this is the these are the two parameters on which your total current will depend. Now, if we want to quantify this current, so we need to understand, or we need to quantify these carriers as well as this mobility, or this overall this saturation velocity, or the velocity of the carriers. We need to quantify if we want to quantify this current. So in the coming this slide, we'll try to quantify these two parameters, because again, once again, just I am repeating, our objective is to find out that rho, or the resistivity. Okay. Again, that rho is also like, or the conductivity is also this three parameter. So now let us see how we can calculate this carrier. So how many? So we'll try to now calculate or quantify. Now we have understood, like if you break the bond, covalent bond, we'll get the carrier. If we dope a semiconductor, we'll get carrier, where we can control the number of electrons and the hole differently, which is not possible in case of thermal generation. So we have understood what is the mechanism qualitatively, but now onwards we'll try to quantify this carrier. So to quantify this carrier, just I'll explain all this equation. So this is the equation we need to quantify your number of carriers available in the semiconductor. So what are the parameters we need to find out to calculate the number of carriers? So one is the Fermi Dirac Fermi function, Fe, or the probability of finding any particle, or probability of finding electron or the carrier at energy E, and this is the density of state. So like how many states are available per unit in energy for your carriers to be occupied. So what is this concept? Let us now discuss. So the analogy, once again, let us take one analogy. So once again, it may perhaps help us to understand this concept and remember this concept. So these are all the empty seat in a let's say a particular or typical football ground. So these are all the seats. So these are all the seats where spectators can come and watch, let's say, a football match. So these are now, depending on the how many seats are available in a particular ground, that will decide how many viewers, or how many how many people can go and watch the football match live. So then it depends on the how many seats available in the gallery. So this is called the, in case of semiconductor, the same concept is the density of state. That means how many states are available to be occupied by the electrons per unit energy, per unit volume. Remember, there is per unit energy as well as per unit volume. Anyway, from the first term, you can understand this is the density. Density is something we need to deal with this volume. So the density of states is same like the number of chairs available or the seats available within a particular it's a football ground. So now another function is the Fermi function in case of semiconductor. So now let's say for a particular day, like for a particular match, how many seats will be occupied? Like what is the probability of the available seats or the available chairs will be occupied by spectators? That will decide the overall viewers of your ground. So let's say you have 100 seats. So 100 seats may not be occupied by the like entirely. It may not be occupied by the people. So maybe 80% of the seats are occupied. That means 80 viewers will be there. So similarly, in case of semiconductor, we have this function called this probability, or this Fermi Dirac function, which says that out of this available number of states per unit energy, per unit volume, how many of them will be occupied by the carriers? That will be decided by this Fe or Fermi Dirac function. So now obviously if we know both this, how many chairs are available and what is the probability that for a particular day it will be filled up or occupied by the viewer. So if we know that, we can calculate the total number of viewers in this particular let's say football match for a particular day. Okay, so that is why we need to understand this both, how many chairs are available and what is the probability those chairs will be filled up by the viewers. And similarly, we need to, in case of semiconductor, to calculate the number of carriers, we need to understand what are the number of states available in the semiconductor and what is the probability that those states will be filled up by the semiconductor. That is the Fermi-Dirac function. So if we can quantify these two parameters, we can quantify this number of carriers or the number of electron or the number of holes. So again, this is the definition that just I mentioned. So number of states available to be occupied by the electrons per unit volume per unit energy. And okay, so now it is already 53. So now my plan is to derive this, but well, I'll not go further today. So I'll stop here. And today again, as you know, that today is a Friday. So Arpit, have you prepared any numerical?
Sir, I have just prepared for the SCC, BCC, and FCC, so we can discuss
Okay.
it. Take much time.
Fine. So I'll stop here. So students, I'll stop here. So next day I'll try to derive all this density of state as well as this Fermi function. Again, we'll try to understand those two concepts in detail, because remember those two concepts, like understanding those two concepts in detail is very important to understand overall this behavior at macroscopic point of this view. So now Arpit will discuss some numerical problems related to this Miller indices, and I hope then those concepts will be clear. So please attend. So again, apart from that, if you have any other doubt, any question, please feel free to ask me or TS. I'll stop here.
Sir,
Thank you.
can you please upload the slides, the PDFs of whatever you've taught till now? The
Okay,
Moodle
actually,
page doesn't show them.
no, actually, my plan is to complete this particular module. Then only I thought I'll upload. But if you need this anyway, so I'll try to upload. Okay, fine. Because again, once again, you can check the video. So there you can get all this. Anyway,
Sir,
I'll try
because
to.
video, yeah, I mean slides for reference I was asking, sir, because if you upload it in the end, then it will be a heavy load. So if you can
Okay,
upload it day by day, so that would be better.
okay, fine, fine. I'll do that. Okay, okay, fine. Okay, any more question? Any more technical question or non-technical thing? Please let me know. Okay, Arpit, you can start then yours.